Okay, so I welcome us back to the part 2 of the acid, base, and salt lesson that we started. I've done the video for the part 1, so I just want to do the part 2 because in the JAM syllabus it is quite a voluminous topic, you understand. So I had to break it into 2 videos so that you will not become tired of just listening to just one video that is spanning close about 2.5 hours there about it. So we will continue and with the acid base and salt. So previously we have been able to um look at acid. We have defined what acids are. We have defined, apart from just defining, we also gave their physical and chemical properties. We talked about their uses, and their uses across different industries and also in the house, household uses, so to speak. We also touched on the bases and we defined what a base is. We talked about the general properties, the physical properties, the chemical properties of bases. So we looked at that, and then we looked at their uses also. And then we looked at salts. We defined what a salt is. We talked about their general properties. We also looked at their physical and chemical properties, and then we looked at their method of preparation. How do we prepare salt? So we looked at that in the previous lesson. So this time around, we are going to move on to an other aspect of acid, base, and salt. And the learning objective for these for this lesson include the following. By the end of this lesson, students should be able to, one, explain the concept of conductance and molar solution of acids and bases, compare the conductance of strong and weak acid and bases qualitatively based on the ionization in aqueous solution. Number 3, describe the factors that affect conductance, including degree of ionization, concentration, and temperature, and also interpret pH and pOH scale, their relationship and their role in determining acidity or alkalinity. And also to be able to perform basic titration calculations, including determining unknown concentration using the mole concept. And it's also expected that students should be able to analyze the titration curves and select appropriate indicators for different acid-base titration. And also, it is expected that by the end of this lesson, students should be able to balance chemical equations for the hydrolysis of salt and predict the pH of solutions formed, okay? And finally, it's expected that students should be able to classify salt based on their hydrolysis behavior into acidic salt, basic salt, neutral salt, and understand their practical application. So let's dive into the lesson now. Okay. Conductance is the ability of a solution to conduct electricity. Now, which depends on the presence of ions and their mobility. So basically, conductance is the ability of a solution to conduct electricity, and this is dependent on the presence of ions and their mobility. Now, conductance of molar solutions of acid and base is influenced by their degree of ionization in aqueous solution. Strong acid and bases ionizes completely, leading to high conductance, while weak acid and bases only partially ionizes, resulting in lower conductance. So when we look at the strong acid, you discover that they have high conductance rates. And the reason is because they have the ability to ionize completely, compared to weak acid or weak bases that do not, ionize completely. And as such, their conductance level is also what reduced now. Now let's look at strong acids and their conductance now. Strong acid completely dissociates in aqueous solution, producing a high concentration of hydrogen ion. Example include hydrochloric acid is a strong acid. So what happens is that when we have strong acid, they dissociate completely in solution and they produce high concentration of hydrogen ion, So we have acid like hydrochloric acid, sulfuric acid, nitric acid. Now, when we take hydrochloric acid as an example, you have, H plus and Cl minus, dissociating in solution, when they ionize like that, and they ionize into hydrogen ion and chlorine ion in solution. Since all the molecules ionize, the solution exhibits what? High conductance. So all their what's it called? Molecules ionize. So we have a strong acid, typically showing what? Strong conductance or high level of conductance use. So that's that for that. Now, when you look at weak acids and their conductance on the other end, because what we are trying to do basically is just that we are just trying to qualitatively compare the conductance of molar solution of strong and weak acid and bases, So that's what we are doing basically. So when you look at weak acids now and their conductance, you discover that weak acid only partially dissociates in water, leading to lower ion concentration and conductance. Example includes acetic acid, carbonic acid, phosphoric acid. These are all weak acid. And when they dissociate, their dissociation is not complete. It's a partial kind of dissociation. So you discover that their conductance is also impacted also negatively. So their conductance is also reduced or lowered, is lowered or reduced, because of their inability to completely ionize or dissociate. Okay. Now, looking at bases on the other end, and we are looking at strong base and their conductance now. Now, strong bases dissociate completely into hydroxide ion and their corresponding cation. Examples include sodium hydroxide, potassium hydroxide, barium hydroxide, and so on and so forth like that. Now, when you have sodium hydroxide, for sodium hydroxide, you have a dissociation into sodium ion and then hydroxide ion. So since the dissociation is complete, the solution has high conductance. They have high conductance, okay? All right. So for weak base on the other end, and their conductance, you discover that weak bases partially dissociate in water. So they produce fewer ions and lower conductance. Examples like ammonia, and then methylamine is an example of a weak base. And when they dissociate, they dissociate and they produce, fewer ions, and then they show lower conductivity or conductance. Okay. Okay, so we have talked about the qualitative comparison of conductance of solution of stronger acids and weaker acid, and their bases as the case may be. So basically, what we are saying is that bringing everything home now, the qualitative conductance of molar solution can be summarized as for strong acid like HCl and H2SO4, they have what? A far greater, conductivity, compared to weak acid. So they show better conductivity or conductance compared to weak acids like ethanoic acid. The same thing applies for strong bases also, like sodium hydroxide and potassium hydroxide. They show a high conductance compared to their weak bases like ammonia, which shows lower conductance. Okay, all right. So what are the factors that affect conductance now? Several factors influence the conductance of acids and base and solution. The first one is degree of ionization. Strong electrolyte fully ionizes, whereas weak electrolytes only what? Partially ionizes. So this will affect their conductance. Another example is concentration. As dilution increases, the conductance of weak acid and bases increases due to increased ionization. And this is based on the Oswald's dilution law, you understand? So that's regarding concentration, which is the factor that influences the conductance of acid and base in solution. Temperature is another factor. The higher the temperature, it will increase the ion mobility. Ion is able to move very freely, leading to higher conductance. So when the temperature is increased, the ion mobility will increase. And when the ion mobility increases, it will lead to higher conductance. So we should also take note of this, or take note of this. So please, we have looked at conductance, and we have looked at a qualitative comparison between strong acid, weak acid, conductance, strong base, weak base, conductance, and also the factors that influences conductance of acid and base solution. Okay, let's move along now and talk about the pH and then the pOH. Now, pH and pOH scale are logarithmic measures used to express the acidity or alkalinity of a solution. So they are used to express, the acidity or alkalinity of a solution. They are based on the concentration of hydrogen ion and hydroxide ion in aqueous solution. So pH stands for potential hydrogen, and it is measured, or is a measure of the concentration of hydrogen ion in solution. Is a measure of the concentration of hydrogen ion in solution. pOH, on the other hand, stands for potential of hydroxide, and measures the concentration of hydroxide ions in a solution. It measures the concentration of hydroxide ions in what? In a solution. So both scale, that is the pH and the pOH scale, range from 0 to 14 at a standard temperature of 25 degrees Celsius. That's the room temperature. And they are related by the equation. What is the equation? pH equals to minus log hydrogen ion concentration. pOH equals to minus log hydroxyl ion or hydroxide ion concentration. So at 25 degrees Celsius, the ion product of water, that's the Kw, is equals to hydrogen ion, concentration of hydrogen ion, multiplied by the concentration of hydrogen of, what's it called? The concentration of hydroxide ion, which will be equal to 1.0 times 10 raised to power minus 14. So please, we need to understand this, because we're getting into a little calculation, and I don't want you to get confused. The pH equals to what? Negative logarithm of hydrogen ion concentration. The pOH is negative logarithm of hydroxide ion concentration, right? Now, at 25 degrees Celsius, which is the temperature at the room temperature, the ion products of water, which we call Kw, it is equal to hydrogen ion concentration multiplied by hydroxide ion concentration, which equals to 1.0 times 10 raised to the power minus 14. Thus, if the pH of a solution is known, the pOH can be determined, and vice versa. Okay, so that's very, 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 very correct. So if you know the pH, you can look for the pOH. If you know the pOH, you can look for the pH using the product of water, which is the Kw. So all I just need to do is just key in the pH, look for my hydrogen ion concentration, and then use that to calculate, calculate further, and then I can always get whatsoever it is that I'm looking for. Okay, so pH and pOH scale interpretation now. Acidic solution have pH that is less than 7. High hydrogen ion, and then the low hydroxyl ion. That's for acidic solution. For neutral solution, they have a pH that is equal to 7. Their pH is equal to 7. The hydrogen ion concentration and the hydroxide ion concentration. And this neutral solution, a very good example is what we see in pure water. You understand? So where you have the hydrogen ion concentration equaling or being equalized or equal to the hydroxide ion concentration. For basic solution, on the other hand, they have pH that is greater than 7. They have pH that is greater than 7, and this table has done good justice to this pH and pOH scale interpretation. When you have a pH between 0 and 3, that solution is said to be strongly acidic. When you have pH between 4 to 6, it is weakly acidic. And when you have a pH that is 7, it is neutral. A pH that is between 8 to 10 is weakly basic, and then that between 11 to 14 is strongly basic. So that's that for that. Okay. Let's move along and do some calculations of pH and pOH now. Example 1, calculate pH from this hydrogen ion concentration. It said find the pH of a solution where the hydrogen ion concentration equals to 1.0 times 10 raised to power minus 3 molar. So the solution, we have the pH equals to minus log 1.0 times 10 raised to power minus 3. So the pH for this particular solution is 3. Since pH is less than 7, the solution is what? Is acidic. The solution is acidic. Okay. All right, let's look at another example that is calculating pOH from OH minus. Now, it says find the pOH of a solution where OH minus equals to 1.0 times 10 raised to power minus 5. Now, the solution to this problem, you have a pOH from our formula before says that is minus logarithm of hydroxide ion concentration, right? So that means pOH will be what? Equal to minus log 1.0 times 10 raised to power minus 5. When you punch this in the calculator, you'll be having a pOH value of 5. Now, since the pOH is what's it called? Since pOH is greater than 7, the solution is basic. Is basic. So we say it is basic, okay? The next one is find the pH from pOH. A solution has a pOH of 4. What is its pH? It has a pOH of 4. What is its pH? pH plus pOH equals to 14. Bear that in mind. So therefore, pH will be equal to what? 14 minus 4, which will be equal to 10. So the pH for that solution is what? Is 10. Now, since the pH is greater than 7, the solution is said to be basic. Now, how do we then find hydrogen ion concentration from pH? This is another problem that we are faced with, or we are asked in questions. So we say the pH of a solution is 6. What is the hydrogen ion concentration of that solution? Don't forget that the hydrogen ion concentration will be what? Will be equal to, according to what with the formula we've been able to establish, we said pH is negative log hydrogen ion concentration, right? So if I'm looking for, if I'm given the pH and I'm looking for the hydrogen ion, so I just need to do a reverse logarithm of the pH value that has been given to me. And when I do that, I'll be having an hydrogen ion concentration of about 10 raised to power minus 6, So therefore, the hydrogen ion concentration is 1.0 times 10 raised to power minus 6, okay? So how do we find OH minus from pOH? The pOH of a solution is 9. What is the OH concentration? If the pOH of a solution is 9, the pOH of that the OH concentration will be equals to 10 raised to the power minus pOH, and that will be 10 raised to the power minus 9. So the hydroxide ion concentration is 1.0 times 10 raised to the power minus 9 molar. Okay, so that's that concerning that. So please, it will help you if you can also look for other questions, that you can try, other problems that you can solve, revolving around these scenarios that I've brought out questions for you, and I've solved the questions. So please get some for you on your own and do justice to them so that it will help your ability to, to retain the information and to be able to recall it easily when you need to to do that. Okay, so we look at acid-base titration now. Acid-base titration. And we say acid-base titration is a quantitative analytical technique that is used to determine the concentration of an unknown acid or base by reacting it with a base or acid of known concentration, which we call standard concentration. So the reaction between an acid and a base lead to neutralization, forming a salt and water as products. Now, there are different types of acid-base titration. The first type is what we call the strong acid versus strong base titration, in which we are bringing HCl and we are titrating with sodium hydroxide. The next one is a strong acid versus weak base titration. like HCl and ammonia. Then the third one is the weak acid versus strong base, which is like CH3COH and sodium hydroxide. And then the weak acid versus the weak base, which we see when we titrate ethanoic acid and ammonia together. So these are the different types of acid-base titrations that we have. Okay, so let's move along now and talk about identification of appropriate acid-base indicator. Identification of appropriate acid-base indicator. Now, when you do titration, there's always a need to use a particular substance that we call an indicator. The whole essence of using the indicator is because you want to know what the endpoint is. You want to get the endpoint of the titration. So you need to use an indicator, but you don't just use anyhow indicator. You have to be careful and you carefully select an indicator that is suitable for the nature of the acid and the base that you are titrating. So that is why it is important for us to identify the appropriate acid base indicators, that we can make use of when we are doing titration. So we say indicators are basically substances that change color at specific pH. They help to determine the equivalence points in a titration. The selection of an indicator depends on the type of acid-base reaction that we have taking place. Now, based on the type of acid-base reaction, then we will select the appropriate indicator. Now, let's look at this table now. If you have a strong acid reacting or being titrated with a strong base, we can use any indicator. Indicators like phenolphthalein will be okay. Methyl orange will be wonderful. When we use phenolphthalein, the color transition will be initially it will be colorless, but it will turn to pink at a point when the endpoint is about to be to reach it to be reached, and then it completely becomes pink at the endpoint. Okay. For methyl orange, you have a transition from red to yellow, now, when we have a strong acid and we are titrating with a weak base, the appropriate indicator to use is methyl orange. And you have a color transition from red to yellow. Now, when you have a weak acid and you want to titrate against a strong base, the appropriate indicator is phenolphthalein. And what we have is a color transition from colorless then to pink at the end point. Okay. This when we also have what's it called? A weak acid being titrated against with a weak base, no sharp color change can be seen. So pH meter is recommended in this regard, So we cannot really say, okay, use this particular indicator because, you may not be able to get the right thing. But the pH meter will be the most appropriate, to use, when you have a titration that has to do with a weak acid and a weak base. Okay, all right. Let's move along now and try to look at interpretation of titration curves. Titration curves graphically represent the pH changes during titration. It represents the pH changes during what? Titration. Now, when you have a strong acid and a strong base titration, what you see is a sharp rise in pH at equivalent points. Is a sharp rise in pH at equivalent points. And that equivalent point most of the time is approximately about 7, pH of 7, weak acid and strong base titration. What you experience is a gradual increase in pH, then the equivalent points above the pH, there's a gradual increase like that. When you have a strong acid and a weak base titration, you also notice a gradual increase with an equivalent point below the pH 7. Then when we have a weak acid and a weak base titration, no sharp inflection points. The pH meter is preferred in this regard. So please, let's take note of that as we look at simple calculations based on the mole concept. Simple calculations based on the mole concept. Okay. Just a minute. Simple calculation based on the mole concept. Yeah. So, well, welcome once again. We will continue the part 2 of the acid-base salts topic that we started. I'd made an initial video for acid base and salts, and In that video, we looked at acids. We defined what an acid is. We looked at the general properties of acids. We equally looked at the physical and chemical properties of acid. Then we classified acids. We gave different methods for classifying acids. So we had a classification of acids. Then after that, we talked about the uses of acid, both industrial usage and domestic usage, So we looked at that in the former video. Pardon me, please. So in the we also looked at bases. We defined them. We also gave a classification for bases. We equally looked at the properties of bases, both physical and chemical. Then we also looked at the usage of bases or uses of bases, industrial, domestic, and medical uses of bases. We touched on salt also, and we said that we defined what a salt is. It is formed mostly from the reaction of an acid and a base. We give different types of salts that we have: the acid salt, the neutral salt, the what's it called, the basic salts, and so on and so forth, like that. We also looked at the various methods for preparing salts: precipitation method, double decomposition, titration method, direct method of preparation, and so on and so forth. We also looked at the uses of salts, and we then wrapped up the video for the part 1 of the acid, base, and salts. So what we're going to do with this one, this particular video, which is the continuation, the part 2 of acid, base, and salt, is to look at the following based on our lesson objective. So let's dive into the lesson objective as we proceed with this lesson now. So it is expected that by the end of this lesson, that students should be able to explain the concept of conductance in molar solutions of acids and bases. And so we need to compare compare the conductance of strong and weak acids and bases. So you do a qualitative comparison to describe the factors that affect conductance, and then interpret pH and pOH scales, and to look at the relationship that exists between them, and also perform basic titration calculations, analyze titration curves, and select appropriate indicator for different acid-base titrations, balance chemical equation for the hydrolysis of salt, and predict the pH of solutions formed, and then classify salt based on the hydrolysis behavior. So these are some of the things that we're going to be touching as we go in this video. So the first thing is to do an introduction into what conductance is, and after that, I'll do a qualitative comparison of the conductance of molar solution of strong and weak acids and base. So let's look at what conductance is. We said conductance is the ability of a solution to conduct electricity, which depends on the presence of ions and their mobility. So conductance of molar solutions of acid and bases is influenced by their degree of ionization in aqueous solutions. Okay. Strong acid and strong base ionize completely, and that leads to them having high conductance, while weak acids and weak base ionizes partially in solution, which results to their reduced or lower conductance. Okay. So when we look at strong acids and their conductance now, strong acid, like I said earlier, completely dissociate in aqueous solutions, producing a high concentration of hydrogen ion. And example is hydrochloric acid is a strong acid, sulfuric acid, and then nitric acid. Now, let's focus on hydrochloric acid and look at the dissociation of hydrochloric acid. When hydrochloric acid dissociates in water, it will dissociate into hydrogen ion and chlorine ion, okay? Having done that, we discover that because there's a complete ionization or dissociation in water, it will exhibit what? A high conductance. It will have a high conductance, okay? The reverse is what we have with weak acids. Weak acids partially dissociate in water, leading to lower ion concentration and conductance. So examples of weak acids like acetic acid, carbonic acid, phosphoric acid, and focusing on acetic acid now, when it dissociates in water, what we have is a CH3COOH dissociated a forward and a backward reaction, then giving us a CH3COO, that's the acetate, and then the hydrogen ion that is now released. You get. So now when that happens, you discover that because the dissociation is not complete, it will impact on the conductance of weak acid. So weak acid, basically, because they have partial dissociation in water or in solution, they tend to have reduced conductance compared to their strong acid counterparts. You get. All right, so that's regarding that. So the strong bases and their conductance, just like we have with strong acid, strong bases dissociate completely into hydroxide and their corresponding cation. Examples include sodium hydroxide, potassium hydroxide, barium hydroxide. Now, when you look at sodium hydroxide precisely, it will dissociate into sodium ion and then hydroxide ion in solution. Now, because the dissociation is complete, the solution has high conductance. So the conductance for strong bases is high also. So let's take note of that. Very, very important that we understand this. Very, very important. Okay. So we move along now and we look at that of weak bases now. Weak bases and their conductance, just like their counterpart, I mean weak acids now. Weak bases partially dissociate in water, producing um fewer ions. So they produce fewer ions and then they have lower conductance. So when you have a weak base like ammonia, when it dissociates, it will give us ammonium ion or ion and then hydroxide ion. So only a small fraction of ammonia molecule reacts with water, leading to lower conductance. So if we try to summarize now, as in summarize the qualitative comparison of weak acid, strong acid, weak base, strong base conductance, you discover that strong acid have a far higher conductance, than weak acid. Why strong bases have a far higher conductance than weak bases. So, and basically the difference is just due to their complete ionization of strong acid and strong bases compared to weak acid and weak bases. Okay. All right, let's move along now and look at factors affecting conductors. There are certain factors that affect conductors. Number one is degree of ionization. When strong electrolytes fully ionizes, strong electrolytes fully ionizes, whereas weak electrolyte only partially ionizes. So when there's a partial ionization, the conductance will be impacted negatively. When there's a higher ionization, the conductance will be impacted positively. Okay. Another factor is concentration. As dilution increases, the conductance of weak acid and bases increases due to increased ionization. And this is based on the Ostwald's dilution law. Okay. Another factor is temperature. When there's an increase in temperature, ions have the ability to move more. There's ion mobility, increased ion mobility. And this leads to what? Higher conductance. So these are some of the factors that affect conductance. Okay. All right. So we move along now. We talk about pH and pOH. Now, the pH and pOH scales are logarithmic measures used to express the acidity or alkalinity of a solution. They are based on the concentration of hydrogen and hydroxide ion in aqueous solution. pH stands for potential of hydrogen and is a measure of the concentration of hydrogen ion in a solution. pOH stands for potential of hydroxide and measures the concentration of hydroxide ion in a solution. Now, both scales, that is the pH and the pOH, range from 0 to 14. as standard temperature, which is the standard room temperature, 25 degrees Celsius, and they are related by this equation. For pH equals to negative logarithm of hydrogen ion concentration. POH equals to negative logarithm of hydroxide or hydroxyl ion concentration. Now, at 25 degrees Celsius, the ion product of water, which we refer to as Kw, will be equals to the hydrogen ion concentration multiplied by the what? The hydroxide ion concentration. Hmm? And that would be equal to what? 1.0 times 10 raised to power minus 14. Therefore, if the pH of a solution is known, the pOH can be determined and vice versa, as the case may be. Okay. All right. So please take note of this relationship, this formula. Very important. We are going to use it more as we go along in the slide. Okay. So if you look at this table, it's gives us an interpretation of the pH and the pOH scale. So when you have a pH between 0 to 3, it means that that substance or solution is strongly acidic. When you have a pH ranging from 4 to 6, it means that it's weakly acidic. When you have a pH of 7, it means that that solution is neutral. When you have a pH between 8 to 10, it means it is weakly basic. And then from 11 to 14 shows strongly basic solution. Okay. All right. So let's take some calculations. Like I told you, we're going to be deploying that formula that we talked about earlier. And we'll be using it in all these calculations that we are going to be looking at. So the first one is calculating pH from hydrogen ion concentration. The question says that find the pH of a solution where a hydrogen ion concentration equals to 1.0 times 10 raised to power minus 3 molar. So the pH is the negative log of hydrogen ion concentration. When you fix that in, you have a pH value of 3 after you have punched it in the calculator. Now, because the pH is less than 7, the solution is acidic. Okay. Let's look at the second question, calculating pOH from OH minus. Now, it says find the pOH of a solution where the hydroxyl or hydroxyl ion concentration equals to 1.0 times 10 raised to power minus 5. Now, the pOH equals to minus log 1.0 times 10 raised to power minus 5, which will be equals to 5. So that's that. So we look at the third question. It says finding pH from pOH. So the question says that a solution has a pOH of 4. What is its pH? Don't forget that pH plus pOH equals to 14. We have established that. So if pH plus pOH equals to 14 and we have a solution having a pOH of 4, that means that the pH will be equal to 14 minus 4, which will be equal to 10. Now, since the pH is greater than 7, the solution is basic. Okay, all right. So let's look at this next one, the fourth one, finding hydrogen ion concentration from pH. Now, the pH of a solution is 6. What is the hydrogen ion concentration? If the pH is 6, what is the hydrogen ion concentration? Don't forget the connecting formula. pH equals to negative logarithm of hydrogen ion concentration. So for me to get the hydrogen ion concentration, it's just the anti-logarithm of the pH value that has been given to me. So when I plug that in, I will get 10 raised to the power minus 6 molar. So therefore, the hydrogen ion concentration is simply what? 1.0 times 10 raised to the power minus 6 molar. Okay. The fifth one says that finding hydroxide concentration from pOH. Now, the pOH of a solution is 9. That's the question. What is the hydroxide ion concentration? The hydroxide ion concentration, like I said, like we have established before, we said pOH equals to negative logarithm of OH concentration, right? Hydroxyl ion concentration. So for me to get hydroxyl ion concentration, just to do an anti-logarithm of the pOH value that was given to me, and I will end up having 10 to the power minus 9 molar from my calculator. So it implies that the hydroxide ion concentration is 1.0 times 10 raised to power minus 9 molar. So that's very good. So please, I want you to, on your own, go back, look for problems regarding, this pH, pOH, and all that, and make sure that you solve them so that you can become a master when it comes to this kind of problems. So please Make sure you do that, and you will be able to scale through any problem that you have been given. Don't forget, just go with the formula, understand the formula, know how to manipulate the formula to get what you are looking for. When I mean manipulating, it means that how to make one the subject of the formula while you're looking, while you have the other one. So you must know how to interchange them and to get your answers, out. Okay, let's move along now and look at acid-base titration. Acid-base titration. This is a very, very important one, acid-base titration. So we are going to look at it, and we say that acid-base titration is a quantitative analytical technique used to determine the concentration of an unknown acid or base by reacting it with a base or acid of known concentration, that is of a standard, a standard solution, so to speak. So the reaction between an acid and a base leads to neutralization, leading to the formation of salt and water as the product. There are different types of acid-base titration, and we're going to consider about four of them in this lesson. The first one is the strong acid versus strong base titration. Example, you're titrating HCl and sodium hydroxide. The second one is the strong acid versus weak base. You're titrating HCl versus, NH3. The third one is the weak acid versus the strong base, in which you're titrating ethanoic acid and sodium hydroxide. And then the weak acid and the weak base is the fourth type of acid-base titration, whereby you're titrating ethanoic acid and ammonia, together, which are weak acid, and they are weak acid and weak base. Okay, so these are the types of acid base titrations that we have, and for us to be able to go through titration, it is important that we take note of the fact that when titration occurs, leading to the formation of salt and water, which we call a neutralization reaction, there's something that we must include in our reaction vessel to tell us when indeed neutralization has occurred. That substance that we use is called an indicator. So indicator is what we use to identify when the endpoint has been achieved or has been arrived at. So we want to identification of appropriate acid base indicators now indicators, like I said, are substances that change color at specific pH, helping to determine the equivalent points or in a titration. The selection of an indicator depends on the type of acid base reaction, so we don't just use anyhow indicator. We carefully consider the reacting acid and base. Is it a strong acid and a strong base? Is it a weak acid and a weak base, as the case may be? And then we now choose the appropriate indicator. Now look at this table now. Strong acid versus strong base. If you have that kind of titration, you want to do that kind of titration, you can either use phenolphthalein or methyl orange. So the color transition for phenolphthalein is from colorless to pink. Now for methyl orange is from red to yellow. That's for methyl orange. Now when you want to do a titration between a strong acid and a weak base, the most appropriate indicator is methyl orange. And for us to be able to use that, you would notice a color transition that is red initially, but once the endpoint or the equivalent point is approached or is being approached, you see the solution turning to yellow. The other type of titration is the weak acid versus the strong base. The appropriate indicator is phenolphthalein, and it transits from colorless to pink at equivalent points. Then we have the weak acid versus the weak base. For us to be able to titrate the weak acid versus the weak base, we may not be able to get a suitable indicator, but the pH meter is very, very recommended and is the most appropriate to be used when we are titrating a weak acid and a weak base. Okay, all right. So let's move along now and look at interpretation of titration curves. Titration curves graphically represent the pH changes during titration. When you have a strong acid and a strong base titration, what you see is a titration curve that has a sharp rise in pH at equivalent point. So it rises and moves up like that from the origin. It sharp has a sharp rise at equivalent. At the equivalent point, it has a sharp rise, Then when we have a weak acid and a strong base titration, there's a gradual increase in pH and equivalent points above the pH 7. When we have a strong acid and a weak base, the titration curve gradually increases with an equivalent point below pH 7. And then when you have a weak acid and a weak base titration, no sharp inflection points. pH meter is preferred to be used for this kind of titration. Okay, we need to now look at some simple calculation based on the mole concept. This is part of the subtopics that we are supposed to treat under acid, base, and salt. So simple calculation based on the mole concept. Now, to determine the unknown concentration in an acid-base titration, we apply the formula M1 V1 equals to M2 V2, where M1 is the molarity of the acid, the initial molarity of the acid, and V1 is the initial volume of the acid. M2 is, sorry, pardon me, scratch that. Let's go over it one more time. I think I made a mistake. Sorry. Let me quickly correct that so I don't pass on an erroneous information. So we use the formula M1 V1 equals to M2 V2, where M1 is the molarity of the acid, V1 is the volume of the acid, M2 is the molarity of the base, V2 is the volume of the base. Okay, so please let's take note of that. Molarity of the acid, M1, volume of the acid, V1, molarity of the base, M2, V2 is the volume of the base. Okay, all right, now let's move along now and look at some examples. There's a question here that says that if 25.0 ml of 0.1 molar HCl is required to neutralize 50 ml of sodium hydroxide. Find the concentration of sodium hydroxide. Now, bringing that our formula to bear now, and we say that our M1, M2 equals to M1 V1 equals to M2 V2. Now, for our M1, it has been stated that it is 0.1 molar, and our V1 is 25 mils, okay? So that will be equal to the M2, which is the unknown molarity that we are looking for. That is the concentration of the base, multiplied by the volume of the base that participated in the reaction, which was 50 mils. Now, when you do the calculation and then you make M2 the subject of the formula, you have your M2 to be equal to what? 0.05 molar. Therefore, the concentration of sodium hydroxide is 0.05 molar. Okay, so it's very simple, straightforward. Just getting the values, plug them in, make one the subject of the formula, and then you get the unknown, and that is that for that. Okay, let's move along now and look at other calculations. This example says that we should look for the unknown concentration of finding the unknown concentration of an acid. The question is, a student titrates 50 ml of H2SO4 of an unknown concentration with 0.2 molar sodium hydroxide. It takes 40 ml of sodium hydroxide to reach the equivalent point. Find the molarity of the sulfuric acid solution. Okay. Now, solution is this. Since sulfuric acid donates 2 hydrogen ion per molecule, the balance equation for this particular reaction will be H2SO4 plus 2 sodium hydroxide to give us Na2SO4 plus 2H2O. Now, using the mole concept, we have our M1 V1 multiplied by N1 will be equals to M2 V2 multiplied by N2. Our M1, we don't know, which is the molarity of the acid that was not given. Our volume for the acid was given to be 50 mils, while the molarity of the base 0.2 molar, and then the volume of the base 40 mils. Then the number of what's it called? Number of acid that was needed is just one, as the number of moles of the acid that reacted is one, whereas the number of moles of the base that reacted is two, So based on that, we bring in our formula We make our M1 to be the subject of the formula, and then if you do the calculation properly, you will end up having 0.32 molar. So the molarity of H2SO4 in that particular titration is 0.32 molar, 0.32 molar. If you are confused on anything that we have been sharing or that I've shared so far, please let me know in the comment section. I will address your question and I will respond appropriately to whatsoever it is that is confusing to you. All right, thank you. So we move along now. We move into the third example now. This one is determining volume required for neutralization. Determination of volume required for neutralization. Let's look at the question. How many moles of 0.5 molar potassium hydroxide are required to completely neutralize 25 moles of 0.2 molar HNO3? Now, first, we need to write a balance equation. HNO3 plus KOH will because KNO3 plus water, okay? Since HNO3 and KOH react in the ratio 1:1 molar ratio, this formula simplifies to M1V1 M2 equals to what? So M1V1 equals to M2V2. You look at this equation, this formula, you discover that we are not introducing N1 and N2. The reason is because it's a one-to-one relationship. The reason why we introduced N1, N2 was because we had 2 moles of sodium hydroxide reacted with just 1 mole of H2SO4. So for this one, we just go with our N1 V1 equals to N2 V2. Now we substitute the given values. When you substitute it and you make V2 the subject of the formula, you end up having your V2 to be what? 10 moles. You end up having it to be 10 moles. That means that 10 moles of 0.5 molar potassium hydroxide is required to neutralize 25 moles of 0.2 molar HNO3. Okay. All right. So let's look at the next one. Calculating the pH after partial neutralization. Calculating the pH after partial neutralization. Let's look at the question. It says that 50 ml sample of 0.1 molar CH3COH, a weak acid, with a dissociation constant of 1.8 times 10 to the minus 5, is titrated with 0.1 molar sodium hydroxide. Calculate the pH after 25 ml of sodium hydroxide is added. Now, we go stepwise in our solution. The first step is we need to calculate the moles of acid and base. Now, the moles of the ethanoic acid equals to 0.1 molar multiplied by 50 divided by 1,000. That is how we calculate the moles of the ethanoic acid. So we look at the molarity, we multiply it by the volume, and then we divide it by 1,000. So the moles of ethanoic acid that was used is 0.0050 moles. The moles of sodium hydroxide that was added for us to calculate that is the same procedure. The molarity of the sodium hydroxide, which is 0.1, multiplied by the volume of the sodium hydroxide, 25, divided by 1,000. So you end up having 0.0025 moles as the moles of the sodium hydroxide that was added. Okay. Now, since sodium hydroxide partially neutralized CH3, the ethanoic acid, the reaction looks like this: CH3, COH plus, the hydroxide that is being produced from the sodium hydroxide, and then it gives us, what we have there. Now, the remaining CH3CO3 will be equal to what? 0.0050 minus 0.0025. That is, you do a subtraction of the number of moles of ethanoic acid from the number of moles of sodium hydroxide, So when you do that, you will end up having what? 0.0025 moles. So the formed what's it called? Sodium ethanoate, so to speak, or the acetate that is produced is just 0.0025. So because of the fact that it's a partial neutralization that will occur because the acid is a weak acid. Therefore, the new volume will be 50 mils plus 25 mils, which will be equal to what? 75 mils, which will be equals to 75 mils. Okay. Okay, so the second step is to use the Adams-Elsabach equation, which says that pH equals to pKa plus log the conjugate acid and the conjugate base, as the case may be, just divide them like that, the concentration, their concentration. So we were told that the dissociation constant for CH3COH is 1.8 times 10 raised to power minus 5. So therefore, the pKa is minus log 1.8 times 10 raised to power minus 5, which will be equal to what? 4.74. The pH will be equals to 4.74, which is the pKa, plus log of 0.025 moles from the acid and that of the base. When you divide it, that's the concentration of the acid and the base that participated in the reaction. We end up having 4.74 plus log of 1, which will be equal to what? 4.74. Therefore, after adding 25 mils of sodium hydroxide, the pH we will result, or the resultant pH is 4.74. 4.74. All right. Thank you. So I want to look at the hydrolysis of salts now. The hydrolysis of salt. Hydrolysis of salt refers to the reaction of the salt with water, leading to the formation of acidic, basic, or neutral solution. Okay. The process occurs when a salt dissociates into its constituent ions in water. And at least one of these ions reacts with water to produce hydrozonium or hydronium ion or hydroxide ion, altering the pH of the solution. Salts are derived from the reaction of acids and bases, and the hydrolysis depends on the nature of the parent acid and base. Okay, so types of salt based on hydrolysis now. Based on hydrolysis, we can have salt of strong acid and salt of strong base, which we refer to as neutral salt. Example, NaCl, is an example of such type of salt based on hydrolysis. Since neither sodium ion nor chlorine ion react with water, the solution remains neutral. That is, the pH equals to what? 7. Okay. The second one is the salt of strong acid and weak base. Salt of strong acid and weak base. That's the other one, salt of strong acids and weak base. Just a moment, please. Salt of strong acids and weak base. Now, when you have salts of strong acid and weak base, like an acidic salt will be produced. So you can see that. So an acidic salt is produced. Based on hydrolysis, also we can have basic salt, which is formed from the salt of weak acid and strong base. We can also have salt of what's it called? Of weak acid and weak base, and that depends on the K and the KB. So we can have all those types of salts based on what? Based on hydrolysis. Based on hydrolysis. Okay, that's good. So let's move further. Hydrolysis of giving examples. Like take for instance, like ammonium chloride. The parent acid or base, HCl, strong acid, and ammonia, weak base. When they react, reaction, you discover that it will give us ammonium ion and chlorine ion when it dissociates in water. And when ammonium ion dissociates further in water, you have ammonia, and then hydrozonium ion that is being given off. So this results in acidic solution. So ammonium chloride is an acidic salt because when it dissolves or hydrolyzes, it will give us hydronium ion, being given off. Aluminium chloride is another base, when it hydrolyzes in water, it will give an acid, so to speak. So it's an acidic salt. Sodium carbonate is a basic salt, and the reason is because it gives what? Hydroxide ion when it dissolves or it hydrolyzes in water. Okay, let's summarize this lesson quickly. We've talked about conductance of acids and bases. We have looked at strong acids and bases, and then we have compared them with weak acids and weak bases, and we have used that as a yardstick for determining their conductance, saying that Strong acid and strong base will give us high conductance. Weak acid and weak base give lower conductance. And the reason is just based on the ionization. Strong acid, strong base ionizes completely in water or dissociates completely. And for weak acid, weak base, the reverse is the case. Partial dissociation, and that is why their conductance is also affected. We also looked at pH and pOH scale. We looked at what they are. We looked at the formula for calculated pH and pOH and the relationship between pH and pOH. And we saw so many examples, in this regard. Okay, we also looked at the acid-base titration. Um, we defined what the acid-base titration is. We looked at the titration curve and the choice of indicators and so on and so forth. We also looked at hydrolysis of salt, and we used that to describe salt or differentiate salt into acidic, basic, or neutral, salt. So when they hydrolyze it, they also hydrolyze to give either corresponding acid, base, or a neutral substance as the case may be. All right. See, so with that, we've come to the end of this lesson, and I will quickly want to evaluate this lesson. But while I'm evaluating, if you have a question or you have an area you want me to clarify, please put it in the comment section, and then I will do justice to it. So the first question that we have here says that which of the following factors affect the conductance of an acid or base solution? So please look at the options from A to D and tell me what you feel the right answer is. Please put what you think the right answer is in the comment section, and I will react to it. If you're right, I will let you know. If you're wrong, I will equally let you know. Why do strong acids have higher conductance than weak base? So we talked about this during the lesson. Look at the options that we have there and tell me what you feel the right answer is to those questions. Okay. It says, what is the pH of a neutral solution at 25 degrees Celsius? Is this 0? Is this 7? Is it 14 or 10? So put the answer in the comment section. In a strong acid, strong base titration, the equivalent points occur at a pH of less than 7, greater than 7, 7. Depends on the volume. So let me know, what do you think the right answer is to that question? Please put it in the comment section. Thank you very much. All right, let's look at this one. It says the hydrolysis of which salt will result in a basic solution? The hydrolysis of which salt will result in a basic solution? So let me know in the comment section. Is it ammonium chloride, sodium carbonate, aluminum chloride, or potassium chloride? Okay. What is the relationship between pH and pOH in an aqueous solution at 25 degrees Celsius? We talked about this when we're talking about pH and pH scale. So please let me know what you feel the right option is and put it in the comment section. Okay. The next question says, which of the following is a weak acid? So look at those acids. Is it HCl? Is it H2SO4? Is it CH3COH or sodium hydroxide? So please let me know in the comment section. All right. See, you have to do a little calculation with this question. It says a 25 ml sample of 0.1 molar HCl is titrated with 0.1 molar sodium hydroxide. Calculate the volume of sodium hydroxide required to reach the equivalence point. So please get your pen, get your paper. Please do the calculation and let me know what the answer is in the comment section. You notice that I did not put any option to this. It was deliberate, actually. So solve and put the answer in the comment section, and then I will tell you if you're right or you're wrong. All right, see? Thank you for listening. Thank you for watching, and I hope you got a lot from this video. So that brings us to the end of acid-base titration. So we have done acid-base titration part 1 and part 2, which I just concluded now. So please, if you still have any question or you still have any gray area you want me to still touch on, please do well to put it in the comment section and I will do justice to it. Thank you for listening. I will see you in the next video. Okay.